We can figure this out using a very helpful equation here, Q equals mc delta T. Again, the specific heat that we're dealing with here is the amount of heat required to change the temperature of materials proportional to mass and the temperature. So Q is heat in joules, mass in kilograms, specific heat capacity C, and then T is the temperature change. So specific heat capacity then is the amount of heat required to change the temperature of 1 kilogram of a substance by 1 degree Celsius. So for instance, if we had a beaker 1 kilogram, which is 1 liter of water in here, right? And we put heat into it, it would take 4,186 joules for the temperature to increase by 1 degree Celsius. Therefore, C for water is 4186 joules per kilogram degrees Celsius. And each substance has a certain amount of specific heat capacity. So, metals and different other things, right? And really anything has a certain amount of specific heat capacity where you have to see how many joules are there, like in this case, how many joules does it take to increase the temperature by 1 degree Celsius. If you had a 1 kilogram mass, probably equivalent in size like this to that, 1 kilogram of that, it's not going to take nearly as much joules to make that increase by 1 degree Celsius, right? And so it has a much lower specific heat capacity. Here's a table of them. In the middle column, it's the kilocalories for grams or kilograms. I'm going to cross through that. We're really going to be using, for the most part, joules per kilogram degrees Celsius. So in other words, if you had a block of ice, turns out ice is different than liquid water. It takes 2,100 joules to increase by 1 degree Celsius if you have 1 kilogram of ice. If you have a kilogram of aluminum, so a kilogram of aluminum like this, if you put 900 joules into it, it's going to increase the temperature by 1 degree Celsius. And you could look at some of these other substances here. Lead, it only takes 130 joules for each kilogram of lead to make it increase, very low specific heat capacity. Liquid is on the high end here, right, 4,186. And then, other metals are in between. And then, they even include like proteins here, and then the human body, which we have a lot of, made up of a lot of water. So how much heat would it take to raise the temperature of 1.5 kilograms of copper from 19 degrees Celsius to 25 degrees? So this is another form of the same equation here, just rearranged a little bit. So Q equals mc delta T. And we're just, if you divide mass and temperature to the other side, you get C equals Q over M delta T. Same thing. And so, yeah, go ahead and use this chart and use the amount in joules per kilogram degrees Celsius to, figure this out for copper here. And when you're ready to check, you can hit play to continue. Okay, so we should get a value of 3,510 joules as how much energy it would take to increase the temperature from 19 to 25 degrees Celsius. Delta T, remember, it's final temperature minus initial temperature. And then, you have your mass here in kilograms, and then this is the specific heat capacity, 390. So this principle is where we have energy out of one part is going to equal energy into the other. And so to say this kind of very basically, the energy or heat lost by one, right, is transfer one is going to be gained by the other. So this mass is going to cool down. It's going to transfer its energy into that water, and then that water is going to heat up. So the sum of all the heat lost and the heat gain should equal 0. So if we add up all the Q's, all the thermal energy loss, thermal energy gain, that'll all add up to be 0. And we're going to use that as we continue here. So let's take a look at this example. Let's say that we have a mass, we'll just call this rock R, 100 grams. Well, the initial temperature is 75 degrees Celsius, which we'll need in kilograms, which you got here. And let's say we have a calorimeter cup filled with water, 0.5 kilograms of water. The initial temperature of that water is 10 degrees Celsius. And then after we place it in there, the final temperature of them will be 10.398. And so what we want to find out is what is the specific heat capacity of the rock. And so if we set up our sum of the Q's to equal 0, we've got that. And what we're going to do is we're going to take a look at both Q of the water, Q of our unknown substance, X. And when we set this up, we know, we have the mass of the water, specific heat of the water, temperature final minus temperature initial of the water. Then we have mx, so for this rock here, times the specific heat of the rock, T final minus T initial of the rock. And so when we place all our values in there, and make sure that you do this properly here, and be careful with your algebra, you're going to get the final specific heat capacity. So go ahead and solve this, and then when you're ready to check your answer, you can check that here. Okay, so you should get 128.95 joules per kilogram degrees Celsius as this substance, and so very close to one of those ones in the table there. So if we look at that, it's very close to lead, so it's probably lead with a little bit of error in there. And so that's what essentially you should be able to do with a calorimetry lab, is take the substances, get those temperatures, get those masses, and figure out what you have. All right, so 2 kilograms of water, 15 degrees Celsius is mixed with 4.77 kilograms of water. At 75 degrees Celsius, what's the final temperature of the water? So in this case, as we draw these out, we have one that's warmer than the other, the 75 degrees Celsius water. And it turns out you actually use the exact same method, because the thermal energy gained by one should equal the thermal energy lost by the other. And so when we set up this, again, some of the Q's, but in this case we have water and water, right? And so if we split this up into, water 1, water 2, we can find that energy transfer. And so go ahead and pick one for one side, one for the other, and figure out what the final temperature would be. In this case, you have to be careful again with your, your variables here. With this is our unknown right here, T final. And so you're gonna have to be careful with your algebra here to figure that out. So go ahead and pause the clip and give it a shot here, and then when you're ready to check, you can hit play to continue. All right, so we've got our values, multiply those in, and so the big thing here is factoring this, right? We multiply this, this becomes 8372. We'll multiply that into here, then we multiply that into 15, and then we take these two and then multiply it into T final and that into here. So then T finals, and then when our basic numbers are set up there, and so our T final should come out to be 57.273 degrees Celsius. So that's the equilibrium temperature of those two. So in this one, let's say that we actually have a cup that's going to, can influence this here. So we have, our mass of lead here, 0.45 kilograms, starts out at 95 degrees Celsius. We have an aluminum cup. Now this aluminum calorimeter cup will be able to heat up. Up until this point, we've used insulated containers. This one can actually heat up. So the initial temperature of this calorimeter cup is 15 degrees. And then the water inside is 0.4 kilograms. The initial temperature is 15 degrees Celsius. And the water itself is 4,186 joules per kilogram degrees Celsius. So what we want to find out is what is the final temperature of all three. So in this case, and here's some values here. The aluminum is 900 joules per kilogram degrees Celsius. And we've got lead up there as well. So we're going to actually set up all three. We have the sum of the Q's of all three. So, Q of the water plus Q of the aluminum plus Q of the lead, right, equals 0. And so, yeah, why don't you go ahead and try this, figure out the final temperature of all three, the equilibrium temperature of all three, and when you're ready to check, you can hit play to continue. All right, so we should get, and you can check your algebra here if you want to pause it. You should get a final temperature of 17.447 degrees Celsius. So the lead is going to cool down, obviously, right? And then the aluminum cup, which was at 15, and the water that was at 15 is going to increase up to 17.447 degrees Celsius. So when we talk about latent heat or hidden heat, this is a really important idea when we're talking about phase changes. So if we have a substance, let's say like a pot of water, and this water's inside, and we heat it up, there's a point at which it gets to the boiling point, and at sea level, that's 100 degrees Celsius. Now, if you put a thermometer inside, the water, even after you keep heating it, the temperature doesn't increase. It just stays at 100 degrees Celsius. But what happens is these particles, evaporate into the atmosphere, and well, not evaporate, but really boil into the atmosphere. You have some of that, you have evaporation too, but the molecules themselves break apart from the liquid, right? So that heat is actually going in and breaking those bonds. When you freeze something or melt something, right? If you have ice and you have heat coming into it, those bonds have to be broken, and then then you have a puddle of water. And it turns out both of these will be 0 degrees Celsius the whole time, until it all becomes water. So you're putting heat into this, and the ice cube is melting the water. You have there, and both will stay at 0 degrees because that temperature, or that heat, is actually breaking those bonds in there. So this is the key idea here with phase changes. On the molecular level, the heat added is changing the state, and it does not increase the average kinetic energy of the molecules, and that's really important because the average kinetic energy of those molecules is the temperature, right? So what it does is we have those breaking those close bonds that are broken, and then the next phase can occur. And so the molecules are breaking apart, and we see that there. So temperature stays the same in a phase change, and it's really important to see that. I've got a time-lapse video that I show in class of an ice cube melting there, and it stays the same temperature the whole time. So the energy required for material to change, is latent heat again. And when we take a look at, the graph here, this is a really, really important graph looking at the phase changes and really temperature changes of water. So let's say you have water at 0 degree or negative 40 degrees, right? So you have an ice cube at negative 40. Now, if you put heat into this ice cube, if you look at the graph, right, it's going to increase in its temperature, negative 20, and then up to 0. And it's going to take a certain amount of energy to do that. In this case, 20 kilocalories. So this is based on, that scale. Once it's at 0 degrees, though, and if you keep putting heat into it, it's going to start to melt, and it's going to start to be an ice cube and water. And in this case here, this gap to here is 80, so 80 kilocalories, 80,000 calories for this, particular substance is going to melt it. Now, once you have melted water at 0 degrees, and you keep putting heat into it, in this case, 100,000 calories, in between 100 here to 200, then this water is going to increase up to water that is at 100. Now, once it's at 100 degrees and you keep putting heat into it, it's going to stay that same temperature, and you keep adding heat, all this heat, and this water will be turning into steam, and you'll have both at 100 degrees. So water and steam at 100 degrees. And then if you still have all that steam contained and you keep heating it, then that steam is going to increase in temperature. But if you notice on this graph, right, these straight lines, you stay at 100 degrees during that phase change. You stay at 0 degrees with water and ice. And so it's important to see that, during that phase change, it's those molecular bonds that are being broken. Now, we could also go the other way, right? We could also go, from a colder situation to a hotter situation. So, let's say we're coming this way, right? If you have steam at 100, or where's the steam at 100? You have steam at 100, right? And you cool it. What's going to happen is water's going to form, and you're going to have water and steam, but they're still going to be at 100 degrees. So if you're cooling it, it'll still be at 100 degrees. Now, once you get it to this point, it's 100-degree water now, and if you keep cooling it, the temperature is going to drop down to 0, and then you have water at 0. Then if you keep cooling it, then you'll have water and ice at 0 degrees, and so on. So this is completely reversible here. Okay, so the latent heat of fusion is looking at the heat required to change a material from a solid to a liquid. So if we have the latent heat of fusion for water here, 3,000 or 333,000 joules per kilogram degrees Celsius, that would mean if we have a block of ice, and that ice is 1 kilogram of mass, and we put in this many joules, so we'll put in 333,000 joules, we heat this by that much, that will take that 1 kilogram of ice and turn it completely into water. Now what we're assuming here is it's already at 0 degrees. It's already ready to go. We'll look at what happens if it's not ready to go yet. And so this is how we calculate how much heat's required. You know, if we have a different amount, right, different amount of mass, we can use the same latent heat of fusion value here. So let's go ahead and try that here with L7. You can pause the clip and do this, and then when you're ready to check, you can hit play to continue. All right, so in this case, we only have half a kilogram of ice. We have the latent heat of fusion. Should get 166,500 joules as the energy required to melt the ice. Now, vaporization, this one is maybe a little bit easier to remember because this is vaporizing, right? Like from a liquid to a vapor, or if we're reversing, you know, cooling, we're going from a vapor to a liquid. We're assuming that our water is ready and it's already at the boiling point. So this is taking water that is already 100 degrees, and we have 1 kilogram of it, right? It's going to take this many kilograms, this many joules, 2,260,000 joules to be able to turn that into steam. And that's a lot of energy. Here is the equation, Q equals M LV, mass in kilograms, latent heat of vaporization we have here. And so, you know, we get how much energy it takes to turn it into vapor.